Okay, so we're continuing this series of videos which will provide a course review of AP Physics 1, specifically for students that are perhaps reviewing and preparing for the AP exam. And this series won't go into any particular depth for any particular subject or topic, rather, but will provide a wide overview of the concepts and equations that are relevant to any of the topics. So right now we're going to be starting with where we left off on the previous one, which was Newton's laws of motion and forces. Newton's first law of motion is the idea that an object that already has some motion will maintain that motion until some net external force either tries to speed it up or slow it down. And if there are no net external forces, then an object in motion will just remain in motion, or an object at rest will remain at rest. That's Newton's law of inertia, Newton's first law. Newton's second law is most widely used in physics problems. Again, is this concept of a sum of the summing up forces along a particular axis, and that would be the same as finding the x components of all forces and adding up however many you have, remembering that any force to the left would be considered a negative force, and any force to the right would be considered a positive force. And this is sometimes just written F net, but the concept is that you're summing up all x component forces to find if there is an unbalanced force, or if all of the forces are balanced, then the net force in that case would be zero. So let's give some examples. If something is sitting on a table, the sum of the forces would be zero, because the upward force, known as provided by the table, pushing in the upward direction, would be equal in magnitude or equal in quantity to the weight of the object. This would be considered negative mg. This quantity turns up a lot. Should be well familiar with this idea. Is by Newton. It's a force. Your weight is a force, and it's equivalent to mass, which is in kilograms. Just the acceleration of gravity and measured in meters per second squared. In this case, those forces would be equal, but opposite direction. And if you sum them up, as we above, minus mg plus mg would cancel. This is zero. Object is at rest. It remains at rest in agreement with its first law of motion. On the other hand, if there is a balance of forces, same exact cup is on a table, and say that there's, well, still a normal force, upward g, still a gravity force or weight of negative g, and it's still true that the force on the x-axis equals zero, as I just showed on the screen. You might have somebody apply a frontal force, an applied force, let's call it F for a force in the x direction. This would be an unbalanced system, although it's along the y-axis, which means that the object will rise to the floor or to the ground, maintain a particular height. So the y-axis is balanced in terms of the forces along the y-axis. There's unbalanced forces along the x-axis. Specifically, this one right here is unbalanced, and that would be acceleration. That is the next part of specifically his second law, that once you understand the net force, that something will in fact accelerate. This acceleration will occur. The force on object is not, meaning it's unbalanced. That concept of acceleration indicates that the object will speed up at a particular rate, that its velocity will increase by a certain amount. Rate is acceleration. From the previous lesson, recall, was delta v over delta t. If this is a constant acceleration, then your velocity and time, if this was 0 to 1 seconds, 2 seconds into motion, start at rest, fine, velocity 0. If you had 5 meters per second velocity in the first second, then you'd gain another 5 in the next second. This would be 15 meters per second. Concept of constant acceleration, this whole entire curriculum, one is built upon only scenarios regarding, with respect to acceleration, only accelerations where the acceleration is constant. Mark again of constant acceleration, a data table that looks like this: velocity versus time graph. Velocity increases by equal and equal time increments, and when plotted on a velocity versus graph would be linear, with acceleration being equivalent to the slope, delta t. Slope of this, as you can see, is 5. So the acceleration in my table here would be 5 meters per second squared. Okay. This idea kind of have an overarching theme from trying to see how does it fit together with Newton's law, which is the following unit. Well, the acceleration depends upon the net force. In fact, they're proportional. If there's more net force, there's more acceleration. So if force right over here were to double all the way to this amount of force, then the acceleration would double. The y-axis forces would still balance, but the horizontal force has been doubled, acceleration would double. And if I repopulate the idea that we just had on the screen, first second wouldn't have 5 seconds. The first second would have shown a velocity of 8 seconds. So it would have sped up at twice as much rate, twice the rate, which is the acceleration would double if this horizontal force I'm showing, in fact, double. And that was one of Newton's theories, the acceleration proportional to the net force. And he also clearly understood the idea, concept of developed the concept of saying that it related to the mass of an object, and that when you push on something you want to speed up, that rate which speeds on is acceleration is inversely proportional to the mass of the object, which means if the mass is large, the acceleration is low. That's in agreement with intuition. Push on things that are heavy, don't speed up so quick. And he also, and this also implies that if the mass is low, you push on something that's very light, the acceleration will be high. Also in agreement with our intuition. Push on something that's light, it speeds up quickly. Those concepts combine. This here, this first portion and this portion, they produce what's known as the second law. Acceleration is exactly equal to the net force on an object, the mass of that object. And cross multiplied, this provides what's commonly shown as F net equals ma. Okay, moving on. What are some common points that you see relating to forces? Well, one would be hanging on a string. This is an example with a 0, and therefore the upward force, the tension must be balanced with the object's weight. Weight is always mg in magnitude, but downward tension force must be plus mg. In the role of a table, you rest on a table. The table has to press upward with a force equal to the weight of the object on the tabletop. If you instead hang it from the ceiling, the table doesn't anymore press upward and support the weight of the object. Therefore, the tension must absorb that, maintain balance, just like. Okay. Right. What if, on the other hand, there's an angle? These go up on exams. Let's say, for example, there's an object with 2 ropes suspended like this from the ceiling. The rope is pulling the tension force. This rope is pulling this direction with a tension force. If these angles right here, vertical, is the same in both cases, it doesn't have to be, but there are some cases in the AP exam problems where they are, then these two tension forces would be equal. They'd be sharing this load, the weight of the object equally, on both sides. From a more vector analysis standpoint, if this one was called FT1, and this force from the other rope is called FT2, there's still a weight force pulling down. F is negative mg. Independence of motion is this idea that horizontal forces cannot fight fight against vertical forces, and vertical forces cannot fight against horizontal forces. That axis x and y being perpendicular, or orthogonal, they're perpendicular. Any forces on one axis cannot have any effect on forces along the other axis. These are components. Only the vertical components of these tenses can absorb the because we know it's hanging, right? So it's in equilibrium. It means that the net forces directions quantity equals 0, which means that the sum of forces of x have to add up to 0, and the sum, of forces on the axis have to add up. So it means this guy here is pulling this rope to the left with a certain amount of force. He's pulling to the right. This x component is pulling to the right with an amount of force. So these add up to 0. If this was negative newtons, then this would be 5, and those would be 0. If the weight of this object was in fact 20 after computing it through mg, if they equally share the load, they have to both absorb half. That means this particular component would be 10 newtons, which is, and this other component would also be 10 newtons. So that the total upward force, 10 plus 10, 20, balanced with the total downward force, which was also 20. If these angles were given, I don't think they would calculate the magnitude of the in either of those ropes, but had they done, you would be able to work. Okay, if the object is 20 newtons, and this is 10 of that, half of it, and we know what this angle is, then we could technically work out this right here. FTX would be force times theta, and we could work out the magnitude of the tension force by using Pythagorean theorem. The first thing you'd have to do would be this here. In fact, you wouldn't actually use that. You would only have to use a tan if you wanted to work out the x component, this unknown, the x-axis component here, and you'd have to use it. So you'd say, well, tan whatever angle they give you, 20 degrees, is 10 over adjacent. Then you multiply to solve for ftx. Once you had ftx as a number, it would go here, and then you'd have this number, and use Pythagorean theorem to work out the force. Again, I don't think that would be likely to show up here, doing a calculation using all of that geometry, but nonetheless, that's how you do it. If pushing something on a flat surface, here's our flat surface, and some said it's kind of a problem up on the AP exam. It shows somebody, let's say, pushing downward with an applied force. Well, this again has components. This would be the x component force. This downward component would be the y component force, and off at the angle theta. The component that actually would be the x component force, fx. And if there was no friction, as is the case on some simple trajectory problems, then there's no other horizontal forces to balance that out. Thus, as in accordance with Newton's second law, it produces an acceleration as we previously said. So to produce that horizontal, to calculate that horizontal acceleration, you need to know what the x component force is, the mass. Again, we would have to use some geometry. If they gave us the magnitude of 40 newtons and told us that this was a 10-degree angle, you would use 20 cos 10 to work out what that x component force is. Okay, is there still a normal force? Yes, it is, right? There is a force pushing up on us. Is there a downward force known as weight? Yes, there is. Particularly, purposely drawing this as a short factor, negative mg, because all of these vertical forces still have to add up to 0. So if we're pressing down right, like we're showing here, downward pressing force is going to increase this normal force be larger, because you're pressing, when you press down on something, normal force increases. And so therefore, Fay, which is shown in the triangle up there, which is this, plus a little bit of weight, those 2 have to equal the normal force, which is more than it would be if no one was touching it. If somebody releases applied force and just goes away, what will happen to the normal force? Well, the normal force should decrease. There's no one pushing down to increase the pressure of the body more, and this one would now shorten and become exactly as much force as the weight. Okay. If you have ramps, only shape exams quite a bit. If you've got a ramp, if there's friction on it, there is a component of the gravitational force or weight that would point you down. And that would be mg sine theta. This angle here is theta, where mg again or weight. Sine theta is a fraction enough then 1. It tells you that it's enough force pulling you down the hill or down the ramp, some fraction of g. Angle increases, ramp, and you the same box there. A stronger force, I'll draw it as a longer line. It's still computed through mg sine theta, but since the angle has increased and sine functions, if you say, what's sine of 0 degrees compared to sine of 90 degrees? Well, cosine of 0 is 1. Sine of 0 is the opposite. It's 0. Sine of 90 is 1. So, with decimals, I was mentioning. So as your angle increases to a sharper hill, like I've shown here, the angle is the sine portion of the calculation or this function sine continues going larger and larger and larger, producing a larger and larger fraction of your weight, and therefore sine theta is always a larger calculation, which is why it's harder for us to stand on steep hills. There's more of our weight trying to pull us down the hill than there would be if we were on a gentle slope ramp like I've shown here. So it's certainly important to know mg sine theta is a component of force due to gravity that pulls you down a ramp. Is there normal force? It is still a normal force, because as long as you're at rest on a ramp, pressing against the ramp, then the ramp will press again. And that normal force is always perpendicular to whatever surface you're at rest on. Right here is known as mg. This bit right here is the y component of your gravity. And this bit right here is the mg sine theta that we just talked about. It's a force that's down the ramp. Okay, that's caused to slide in that downward direction. And theta in that triangle is the same as ramp angle. And so if you were asked to find the y component, it would go with cosine mg theta. If you find the x component, the one that actually causes down axis, sine theta, mg sine theta. Remember, the x and y axis is normally skewed as such to simplify problems. These two, this normal force is equal to the length of FAY because those cancel. That side down the ramp position cause you to start flying upward curl or sinking downward. You maintain motion along the x-axis. If you're maintaining motion on this x-axis, all the vertical forces along over here to be our y-axis, and parallel to that have to add 0. Well, FAY is parallel to that, and so is the normal force, right? And so those cancel. So that's why the normal force is in fact cos theta. It's the same. This would technically be negative if it was down. This one would be positive. Cool, the concept. Okay. If you happen to be given a friction problem on a ramp, remember that the friction force, specific kinetic friction force, is the coefficient of kinetic friction times the force. So there and back. Let's not do the ramp right away. Let's just do the flat surface. If you're pushing something that's on a flat surface, it's not flat. Let me try again. Here's our flat. So you're pushing. If the motion is to the right, the frictional force to the left. If you're looking for the kinetic friction force, which is use the equation, calculate it. Depending upon how much friction there is between the block and the surfaces that rest on, and it also depends upon how much pressure there is, how much force there is in between the bottom of the box and the surface. And that pressing force is known as the normal force, Fn. So let's know that gravity is mg, negative. Sorry, that looks like 3 equal dashes for the equal sign. That's just showing that negative mg. Force is plus mg, which we already talked about. And so you put in the normal force, friction force, the kinetic friction force would be mu k times n times g in the simplest case when somebody either pushing it to the right, then this is how much kinetic friction force. If somebody pushes it and then releases it, then it's the same amount of friction. Remember that right where applied force has no effect on anything happening along the vertical axis. It doesn't change the normal force. So therefore, normal force doesn't change, and the friction force, the force doesn't change. So you are biking, and then you remove your pedaling force, and you were sliding. I guess biking wouldn't be a perfect example, but a box that's sliding along, and then whoever's pushing it releases it. The frictional force is still mu k times mg. That would turn out to be, if you wanted a sign in there, would have negative to indicate that this force is slowing you down. Your motion is to the right, this frictional force is to the left. That's going to reduce your speed at a certain rate known as deceleration, and you could certainly compute it using A equals F over m for Newton's second law if you had to. If you were applying or looking at static friction is very similar. Force of static friction is equivalent to the static friction coefficient also times the normal force. And there's a maximum. That's often what you're referencing in problems is the slipping point. And the slipping point means that you have something that's on a surface and someone's pushing, and they push harder and harder and harder, making this applied force longer and longer. And at some point, it slips and motion occurs. At that point, the static friction force can't hold on anymore, and it lets go, and motion occurs. You wanted to calculate how much static friction force that is, the maximum holding force between the surfaces. It would be mu s times Fn. And in most simple cases, if everything was flat, like we've shown here, it would be mu s times mg. Which, remember, mg is just the weight of an object. So it's often a fraction of your weight because mu is almost always a number less than 1. Same thing with kinetic friction. Most coefficients of friction, static and kinetic, are all decimals. You can look it up on the tables online or in a textbook. They're almost always decimals. 0.9, 0.7, 0.5. That means that these forces of friction and kinetic friction and static friction are either, if it's 0.5, that would be a force that's 50% of your weight. Because as you're seeing right here, this number is often a decimal, 0.5, 50% of weight. Okay, that's another concept. So now we go over back quickly to ramps. If we're looking at ramps, and we were actually asked about the frictional force. I don't know that you would, but if you were, frictional force of the sliding kinetic friction force is still mu k times Fn. That's always true. And before, we had the Fn, the normal force, equivalent to the y component, Fay, I didn't mean Fay, Fgy, right? And so remember there was this whole triangle we draw, this bit was mg, and Fay is mg cos theta, because this angle here is theta, and this piece that we're looking at, Fgy, is adjacent to that. And so Fn, as I previously said, was mg cos theta, because those are equal and opposite. So that would get plugged in right here, and after you release this object that slides down this frictional surface, if this was friction on this ramp, the frictional force would be mu k times mg cos theta. And it would cause the object to speed up. Friction doesn't cause you to speed up, but it would cause you to speed up at a slower rate than you would if there was no friction. If there's no friction, you fly down that thing and your speed would increase very rapidly. If there is friction, that force will remove the overall horizontal net force, because this amount is your weight pulling you down, mg sine theta, and the amount that's in this direction would be the mu k times mg cos theta. And that would have to be a negative, this would have to be a plus, and there should be some unbalanced amount if you're actually sliding. Maybe it looks like this, and that bit would be called the net force in the x direction, and it would cause you to accelerate down the ramp. Okay, moving on. Let's move on to something slightly different. Planets, gravitational force. This is Newton's law of gravitation. That planets pull on each other with certain amounts of force, and that amount of attractive force, called gravity, between all things, including your body and a planet, or any two objects on our planet, or two actual planets that are floating in outer space, the attractive force known as gravity between those two planets is proportional to the product of their masses, m1, m2, and inversely proportional to the distance between those two planets. So if you've got a planet here and a planet here, center to center is considered the distance between them, not just the surface as you might think. Technically, it goes center of mass to center of mass. That's called the full distance r between the two objects. The gravity attractive force is inversely proportional to that distance. So if these things get closer together, r is now getting smaller. If r is decreasing, then the gravity force will increase because they're inversely proportional. And conversely, if these two things got much further apart, from here all the way to here, then r is now really large, and if the r, the denominator, increases, then the gravity force will decrease, again, because they're inversely proportional. And so that is giving the sense that gravitation is a proximity force. Proximity means it's local. It depends on how far away you are. If you're really, really close, the force is really strong. If you're really, really far away, the force is very weak, like magnets, very similar. These are the proportionalities. There's a proportionality constant called G. I don't think that you'd ever need to use this, but that's the actual value. And when you combine all of those proportions and proportionality constant into one equation, it produces Newton's law for gravitation, which is the in magnitude gravitational attractive force between two planets is equal to G, the constant, capital G, not lowercase g. Lowercase g is the acceleration due to gravity on our planet, 9.8 meters per second squared. Capital G is this really, really tiny number, which is why gravity reflects as to why gravity is considered one of the weakest forces in nature, because the gravitational constant is very weak. That said, G m1 times m2 over r squared. That is his formula. Specifically, you need to know how to answer proportionality questions. If the distance between two objects goes up times 2, then you imagine putting a 2 in here and squaring it, which provides a factor of 4, which means the gravity force will drop. As we previously showed up here, gravity force weakens if they get 2 times further away by a factor of 2 squared, which is 4. So that means if the planets double their distance, the gravity force is 4 times weaker. If the distance between the planets triples, if r goes up times 3, then you imagine putting a 3 down over here and saying, oh, I guess I have to square it since there's a square there. You'd say, okay, 3 squared, oh, that's 9. And so, therefore, if radius triples, that means r is really the physical distance from center of planet to center of planet. If that distance goes up by 3 times, then the gravitational force will decrease again, because they're getting further apart, by a factor of 3 squared, which is 9. So that means the force is 9 times weaker if the distance triples. You could go the other way with it, of course. Instead of things getting further apart, they could say, well, these planets are getting closer. Okay, we can do that whole entire process as well. If the two planets got 2 times closer, well, just start with, if they get closer, what happens to the gravity force? If planets get closer, stronger force. When they're close, it's a strong force. So you develop the idea that, okay, if they're getting closer, r is going to go down, therefore the gravity force is going to go up. They say they get 2 times closer, r is increasing by a factor of 2. You still do the whole thing. 2 squared is 4. Okay, so if r goes down times 2, the gravitational force goes up times 2 squared, which is 4. So that means the gravity force is 4 times stronger if the planets are 2 times closer. Equivalently, if it was 3, planets get 3 times closer together, the gravitational force goes up by 3 squared, which is 9. 9 times stronger of a force. That's called the inverse square law. It occurs for lots of things in physics, including sound waves, light waves, magnetism, electricity. Coulomb's law is also based on an inverse square law, that the force between charges, electrons and protons, or any particular electric charges, the forces they feel as they repel or attract each other is inversely proportional to the square of the distance between them. It's a very common law. It's a very foundational part of physics. Again, it's known as the inverse square law. Let's continue on. Let's say there was circular motion problems. That has to do with forces. So you've got something moving along a circular path. Say like this. It must feel an inward force known as the centripetal force, because centripetal means center-seeking. And therefore, if that inward force is not applied, this object would just float off into space, or fly off in a straight line if it was something on Earth. But in order to keep it on a curled circular path, you need to continually pull inward. Objects here, you got to pull inward. You got to keep pulling inward at all times with what's known as a centripetal force. The centripetal force depends on how massive the object is. If it's a very highly massive object, then you got to pull hard. That makes sense, inward, to maintain a circular path. It also depends on how fast the object is moving. It turns out that it's the square of the tangential velocity that the centripetal force depends on. And it also turns out that there's an inverse proportion with the radius of this actual circular path called r. So that means if it's a very wide path, like our planet Earth is extremely wide, r is huge, it's in the denominator, centripetal force therefore is very, very tiny, which is why we don't necessarily need a lot of extra inward force to be pulling on us to keep us stuck to the planet. It's a very small requirement. However, if you're on an amusement park ride and they're zipping you around on a circular path and r is small, the centripetal force will be quite large, because r is in the denominator again. You put a small value in for r, centripetal force comes out enormous, and that centripetal force is what makes you sick, because it corresponds to a very large centripetal acceleration. Centripetal acceleration is vt squared over r. That's what makes you sick when you're going round and round on a ride. You're feeling that force against your body as they zip you round and round. And if you're on an amusement park ride, v is already fast, because that's the idea of amusement park rides. That causes the acceleration, centripetal acceleration, to be large. And it's a relatively small radius circular path, which even further this idea that the centripetal acceleration is large. So, to review, there is this thing called the centripetal force. It's equal to the mass times the centripetal acceleration. That's noted as F equals ma, in agreement with Newton's second law. Turns out that since the centripetal acceleration is v squared over r, the formula for centripetal force in magnitude is mv squared over r. Portions can always apply. I'm not going to do it for the whole entire lesson, and all these things that I'm planning to record, but if, for example, your velocity doubled, then you can imagine putting a 2 in here, squaring it. That means the centripetal force requirement goes up by a factor of 4. Okay, oops, let's delete that. All right, let me continue looking on this book, because I'm not entirely sure if there's much more to talk about regarding forces. Probably is. Let's see. Circular motion, I did that quickly, which is fine. I think that might be it. I think that might be at least, I can probably shut this down and call this review for forces. Yep, I'm going to call that it. So I'm going to make another one coming up soon for whatever the next unit was. I think the next unit would be momentum. Yep. momentum's coming up next. Hope you found that helpful.